JPL. So the bad news is that our museum area, it's kind of a box area, is actually been turned into a press room, so we can't go in there. The good news is we're on the verge of putting a spacecraft in orbit around Jupiter. And I'll tell you how you can follow along with that, but on Monday night, yes, that's July 4th, at 8:18 p.m., we're going to start a 35-minute rocket burn maneuver that's going to slow the Juno spacecraft around and put it into an orbit around Jupiter. And so that'll be on NASA TV in case you have nothing better to do on the evening of July 4th. This is actually the third time we've had a major mission event on July 4th. So we put a rover on Mars in 1997 on July 4th, and we smacked a slug into a comet on July 4th in 2005, and now this. So for some reason, celestial mechanics requires that all major JPL events occur on nights or weekends or holidays or something like that. So this is actually kind of exciting. This is a quarter-scale model of Juno, and our next stop is going to be down our spacecraft assembly facility, and you'll see a full-size solar panel wing to get an idea how big this spacecraft really is. So just blow this up by a factor of 4 and get an idea. It's a very large spacecraft. One of the things that's special about it is it's actually solar powered. So when you go out into the solar system, when you move away from Earth, the amount of sunlight falls off not by the distance. So if you are at Earth and you move twice as far away, you're not down to half as much sunlight, you're down to a quarter. So it's the inverse square law. So as you've got a bubble of sunlight basically that's expanding away. So if you're at one distance like Earth, you get that much sunlight. If you double the distance, you're down to a quarter. Jupiter's 5 times further away, so we're down to 1/25th the amount of sunlight reaching it. So the amount of solar energy available to work on the solar panels is only about 4% of what you see here. And so that means that the solar panels have to be very, very large and also very efficient. So this is arguably the most efficient set of solar panels you've ever sent into outer space. And that's because there's so little sunlight that you have to capture that. Most of the spacecraft we send out farther out use a radioisotope power source that generates heat that's converted to electricity that doesn't rely on the sun at all. So it's like flying batteries instead of solar cells. So this is a bit of an experiment here to fly a solar-powered spacecraft this far out. It holds the record for doing that. And Oda and Lyle have actually worked on a teachable moment, which we might have shared with you, about inverse square law and how that works. So, make a long story short, the spacecraft is spinning at 3 revolutions per minute right now. It's going to be spun up to 5 revolutions a minute for gyroscopic stability. It's going to position itself with a rocket motor, which is on the bottom part of the spacecraft there in the direction it's going. 35 minutes to slow itself down, and then it's become a satellite of Jupiter for the next couple of years. And it'd be a permanent satellite, except at the very end of the mission, we're actually going to crash it into Jupiter and kind of take out the trash. One of the problems with flying near Jupiter is Jupiter's got it's not only the largest planet in the solar system, it's got an enormous magnetic field. Very, very strong magnetic field. If you could see it from Earth, it would be the size of the full moon. And so that magnetic field traps charged particles that come from the sun and from outer space, and they go whizzing around, they're trapped in these fields, and it produces a whole lot of radiation. So radiation isn't not only bad for us, it's bad for spacecraft components as well. And so over time, the spacecraft's going to be irradiated and it's going to be degraded every time it flies through these magnetic field and trapped radiation belts. And we've got backup systems and redundancy and things like that, but it's going to damage the spacecraft. So to keep it alive at all, the main electronics are in a titanium vault. This is a full-size model of this vault right here, and all the electronics are on the inside of that. That's going to provide additional radiation protection. And so one of the challenges is when you have radiation, it can affect your computers. And so you can be running a computer program, and here comes a stray radiation particle that's moving at almost the speed of light, and it hits a register in the computer and flips a bit from 0 to 1 or 1 to 0, and all of a sudden your program isn't running properly. Well, if you're doing a burn for 35 minutes to go around Jupiter, there's no do-overs. So a better way of thinking of it is if you're going through hell, keep going. So in the case of the spacecraft, if you have a problem, and normal spacecraft operate this way, if you have a problem and there's an issue where the spacecraft's not happy with its condition, it can put itself in a safe mode, where it basically says, okay, something funny's going on here, I'm not prepared to deal with this, so I'm going to protect power generation and communication with Earth. And I'm going to send telemetry back so the people on Earth can figure out what's going on and help me with that. But when you're doing a burn like this, there's no do-over. So we could have a situation where the burn is started and we're like 10 minutes into the burn and something happens and the computer has to reboot. It knows for this burn here to reboot and start the burn again. Don't call Earth and ask for help. And the reason is it takes about 45 minutes to get a signal from Jupiter to Earth. It's so far away. So if the spacecraft says help, by the time the signal reaches Earth, even if you know exactly what to do and send the signal back, that's an hour and a half. Well, if you're doing a 35-minute burn, an hour and a half is just way too long to deal with that. So the spacecraft has most of the fall protection turned off, and a special set of instructions that say, no matter what, continue the burn. Restart, start the burn again. Keep going, keep going, keep going. And then we'll change our behavior in the operation of the spacecraft later after we get into orbit. So this antenna at the top is a communications antenna. I don't know if we have continuous communication on July 4th or whether we just have a signal to get what's going on. But basically, it's not going to be closer until 9 o'clock. We actually know whether the burn has been successful or not. And then below that is the vault with the radiation protection for the electronics. And then most of the body of the spacecraft is propellant tanks. So when we launch spacecraft from Earth, most of their mass is actually liquid, rocket fuel. And then that will be depleted, and then the spacecraft will ideally be in this orbit that we're hoping to accomplish. So the reason why we're doing this mission and flying it in this particular way is Jupiter is the largest of the planets. It formed as the solar system did, at the same time the sun did. And from previous missions, we know that the composition of the interior of Jupiter, down at least a little ways, is similar to that of the sun. So we know we started with this large primordial nebula of dust and gas. Most of it, 99.86% of it, is the sun. And then most of the rest of the leftover is Jupiter. And then there's a lot of miscellaneous debris, like Earth, and asteroids and other lumpy things around. But most of the mass of the solar system that's not the sun is in fact Jupiter. But we don't know why Jupiter's got these cloud bands and why it has, what the interior is like. So by flying the spacecraft around in very close orbit and far away, we're looking at very minute changes in the orbit, and that's going to tell us what the inside of Jupiter is made of, what the layering of Jupiter is made of, because the gravity of Jupiter is what's affecting the orbit of the spacecraft. So if Jupiter were a rigid body, which we know it's not, it would spin as a solid object and the orbit would be very steady. But we know that it's got layers of liquid, and maybe it has a solid core, maybe not. One speculation is that amount of carbon that would have fallen in under compression, there could be a diamond the size of Earth at the core of Jupiter. That'd be awesome. Okay, highly unlikely, but not out of the question. But it's got all these liquid and gaseous layers that are spinning around, and it could be it's a series of cylinders where they're spinning in opposite directions. You see the clouds whizzing back and forth relative to each other. We don't know, but Juno is going to tell us about that. So if it survives the orbit insertion on Monday night, and we get a few science orbits out of this, we'll get a good idea of what the interior of Jupiter is. And over a period of a couple of years, we continue to do that. It's also got a very good camera on board that's meant for basically public outreach purposes. It's not a science camera, but Juno's flying in orbit that's going to carry it over the North Polar and South Polar regions, and we're going to get a good look at those, which we have not from other spacecraft, which have orbited close to the equator or flown by the planet. So there's a lot more to come here. There's already a picture from the camera of kind of looking at a distance down at Jupiter. You can always make out the red spot and the cloud patterns and so on. So pretty cool, major mission event. Totally disrupted the activities of the laboratory, of course, this week. Had some press conferences yesterday and a lot of activity expected on Monday. So if you happen to be going to the Rose Bowl for the fireworks show, there's a Juno, I believe, painted on, full size, painted on the field. And they're going to actually watch some of our NASA TV coverage as part of the fireworks show and the 4th of July celebrations down there. So, kind of cool. All right, so if you guys have any questions as we go